I am Oleg Lychkovskiy. I am working as a senior research scientist in the Skolkovo Institute for Science and Technology, and also in the Moscow Institute of Physics and Technology, and also at the Steklov Mathematical Institute. I am going to talk about our theoretical research funded by Russian Science Foundation on the electron flow through driven quantum point contact. What effects can be observed when this quantum point contact is under the action of time-dependent electric and magnetic fields. You are welcome to ask your questions online, and after the talk I will have 15 minutes to answer them. Okay, so the audience of this forum is, as far as I understand it, is quite broad and diverse. Therefore, I tried to prepare my presentation in such a way that it could be interesting both for experts in the field and for people that simply are interested in the topic with some basic physics backgrounds. So I will start from really simple things, discuss Schrdinger equation, the complexity of quantum manybody problem, the ways to tackle this complexity, and then I will switch the gears and turn to a specific research project I was involved in and describe it, show some more formulas, more equations than in the first part of the talk, but hopefully it will be all understandable. But before I turn to physics, let me make a somewhat philosophical remark. As you could probably guess from the title of the talk, I am doing theoretical physics. Theoretical physics, and more broadly basic science, has a twofold value, a twofold role in the society. First, it is a piece of culture, a part of culture, as literature, arts, or music is. Second, basic science is a basis for technological innovations. This role of basic science is mostly appreciated by funding agencies, governments, business, and so on. But actually, the route from basic science to technological applications is not always linear. So in this slide, you can see a very rough diagram which shows the pipeline from theory to technological applications. First, I will mostly talk about physics here, but I believe this applies to all natural sciences, more or less. So people doing basic science either discover new laws of nature, or more frequently, they discover patterns of behavior of complex systems. These specific patterns are called effects. An effect can be discovered either theoretically or experimentally. If it is discovered theoretically, then it should be realized or tested or verified in an experiment. If it is discovered in an experiment first, then we would like to get a theoretical understanding and explanation of the effect. In practice, this usually takes several rounds of interrelations between theoreticians and experimentalists to fully clarify the effect and to make it well reproducible and manageable in the experimental lab. After this is accomplished, after the experimental techniques are mature enough, the effect might find its applications. When an effect is discovered, it's actually very hard to predict or anticipate whether, if and when it will find technological applications. And this is actually not what people doing basic science are mostly bothered with. So the the job of scientists doing basic science is to produce a rich toolbox of effects, of knowledge about patterns of behavior of physical systems in order for applied scientists and engineers to use this toolbox in future technological applications. The research project I'm going to tell you about is a theoretical project, and we have theoretically discovered a very interesting effect which is waiting for its realization or verification in experiment. And still, even at this early stage, due to some very interesting and very useful features of the effect discovered, we can anticipate that it might find technological applications. And I will discuss this in the end of my talk. Now let's turn to physics. The behavior of microworld is described by quantum mechanics. And the core of quantum mechanics is the Schrdinger equation, which you see on your screen along with the Schrödinger's photo. Schrödinger equation is a linear differential equation that has two ingredients. The first one is the Hamiltonian, and it describes the system. It may or may not depend on time. If it depends on time, this usually means that there are some external classical fields that depend on time, such as electrical or magnetic field. And also there is a state vector, which depends on time and which encodes the evolution of the state of the system. There is also a stationary Schrödinger equation. It can be written if the Hamiltonian doesn't depend on time, and it describes equilibrium state vector. State vector which doesn't depend on time, it is also called an eigenvector. Now, what I'm going to do is to solve a problem from the field of far from equilibrium driven quantum many-body dynamics. And arguably, this is the most complex type of problem one can imagine in physics. And let me explain why. So each of the terms in this specification, far from equilibrium, driven, quantum many-body, dynamics, adds its own level of complexity to the problem. And let's discuss them one by one. First, quantum many-body. If you try to solve the Schrödinger equation on a computer, say, the main figure of merit which characterizes the complexity of the numerical calculation is the length d of the state vector. The Hamiltonian then can be thought as a matrix d times d. The problem is that for many-body systems, d grows exponentially with the system size. And to give you an idea how bad this is, let me give you an example. Imagine you have a system of qubits. Qubit is the most basic ideal system consisting of two levels. There are no ideal qubits in nature. Even the hydrogen atom has many levels, actually, infinitely many levels. However, in certain circumstances, you can approximate your system, fairly approximate it by a two-level system, and then you have an approximate qubit. So let's make the life simpler and imagine you have ideal qubits, n qubits, and this system of qubits is in some arbitrary state. And you want to store this state in your computer, say in your laptop. Then what is the size of the maximal size of the qubit system you can, that you can handle in this way? The answer is 40. If you have a good laptop with 1 terabyte of memory, then you can store the state of 40 qubits, not more. Note that I don't say that you can solve the Schrödinger equation for 40 qubits on laptop. You actually cannot. You need a supercomputer for that. But just the most basic task to store the state, and you cannot do more than 40 qubits. Okay, but we have supercomputers, maybe they can help. Imagine that you have access to all the storage of the whole world, all the supercomputers, laptops, hard disks. Then how many qubits you can handle? The answer is, well, 75. Maybe 74, maybe 76. This depends on the accuracy you want to store the state with, and on the exact estimate of the world storage capacity. However, you see that when just to double the system size, you need the whole storage of the whole world, and still it's not enough. You cannot handle 80 qubits. So this demonstrates that the problem actually is grave. So this implies that you cannot straightforwardly simulate the Schrdinger equation for a many-body system on a computer, on a whatever powerful and fast computer. The next level of complexity comes from the need to consider far from equilibrium dynamics. If we were interested in equilibrium properties, then we could do with stationary Schrdinger equation. This is not a differential equation, and in some sense it is somewhat simpler than differential equation. But we need to describe far from equilibrium dynamics, and so we don't have this option. We are left with differential equation. Even worse, we need to describe a driven dynamics. When I say driven, I mean that the Hamiltonian explicitly depends on time. And this means that your differential equation has variable coefficients. Those who have ever taken a course on differential equations know that solving a differential equation with variable coefficients is much harder than doing that for equation with constant coefficients. So what can we do with this overwhelming complexity? Well, we have to use some approximate methods, and there is quite a number of them. First, you can use a good old perturbation theory if you have a small parameter in your system. Then, if your Hamiltonian depends on time periodically and the frequency is large, then you can use a Floquet-Magnus theory, and I will explain briefly what it is in what follows. You can use various numerical techniques and so on and so forth. And yet, there is another quite different option. You can try to use an exactly solvable model. If you can find an exactly solvable model which describes your system, or a system which is close to a system in some sense, then you can try this route. And this is actually the route which we have taken in our research project. Exactly solvable models have many benefits. First of all, they're beautiful. One of the most well-known books on exactly solvable models, written by Sutherland, is entitled "Beautiful Models." Second, they often allow an in-depth understanding of physical phenomena, which is unfeasible otherwise. Last but not the least, it can be used to benchmark approximate techniques. This means that, well, often physicists come up with an approximate method which they think should work well. Their belief is often based on some physical intuition, but they cannot precisely specify or estimate the errors, the precision of the approximation. If you have a suitable solvable model, you can try to apply the method, an approximate method, to this exactly solvable model to compare an approximate solution with the known exact solution, and this way to estimate the accuracy of the method, or the approximate method. And there is one important issue with exactly solvable models. sometimes they can display non-generic behavior. When I say non-generic, I mean that they have some peculiar features which do not show up if we turn to similar but non-exactly solvable models. I will show that in our project we have found a good exactly solvable model. It displays interesting features which, as we have shown, are actually generic. And we also use it to benchmark approximate techniques and to show which approximate techniques are can be used to describe our problem and which are quite useless. Now, this was kind of introduction. Now let me introduce you quantum point contacts. A quantum point contact is a contact which connects two conductors. It is called quantum because it has small dimension. So this is a constriction of with the size of tens or hundreds nanometers, comparable to the electron wavelength. This means that the transport through this constriction is not governed by the Ohm's law, by the classical physics, but rather by weird rules of quantum mechanics. And one can actually obtain all sorts of weird quantum behavior with quantum point contacts. So in the leftmost figure in the slide, you can see an experimental scanning microscopy photo of a simple quantum point contact. So there are two conductors, two leads, shown in dark gray, and they are connected by a imprinted constriction of small size. So the electrons flow through this quantum point contact, and this flow is described by the rules of quantum mechanics. Quantum point contacts can be driven. This means that time-dependent electric and magnetic field can act within the quantum point contact, and they can be actually quite complex. On the right plot, you can see a more complex quantum point contact. Let me also mention that they can be produced on various technological platforms. This one is a gallium arsenide heterostructure. So in the right, I show a different quantum point contact made of graphene, and in the bottom I show a cold atomic simulator of quantum point contacts, where it is an atom, not an electron, which flows through it. The atoms are confined in optical lattice traps, and there are two such traps, and they're connected by this quantum point contact. So here we have a different sort of particle flowing through the quantum point contact. Still, this is basically the same physics. So this was, I think, the only experimental slide in my talk. Now let's turn to a more quantitative description of the problem. As theoreticians, we love to explore, to start from the most simplified models possible. Therefore, we start from non-interacting fermions. We model our conductors as one-dimensional lattices, and we assume that the quantum point contact consists just of two edge sides of our lattice. So the schematic of this setup is shown in the bottom of the slide. The blue circles are the lattice sides, and the fermions can hop from a side to a nearby side, and two central sites shown in wiggly lines belong to the quantum point contacts. These wiggly lines are meant to mean that the fields are time dependent on these sites. And there is this spherical cow cartoon on the slide. Russian-speaking audience might know a joke about spherical horse in the vacuum. When I prepared this talk, I learned that in the English-speaking world, there is an analog joke about a spherical cow. So since this is a lecture in English, there is a cow on the slide. Now let me present more formulas. The Hamiltonian of the model consists of three parts. There are two boring parts describing just tie-dividing lattices, the left one and the right one. And there is this part V, which depends on time, which describes the quantum point contact. As I have said, the fermions are non-interacting, so the Hamiltonians are quadratic. The most important part here is V, and let us focus on it. As I have said, it depends on time, and this time dependence is encoded in three functions. The first one is J. This is a function of time, and it is actually a hopping amplitude between the site number L and site number L plus 1. Well, I forgot to say that the length of the chain is L, so the site number L is the edge site of the left chain, and the site L plus 1 is the edge site of the right chain. So J stands for hopping, and also we have two on-site terms, U left and U right. And now let me introduce the main hero of our research project, the conformal quantum point contact. The term conformal comes from the conformal field theory, where this type of Hamiltonian was first considered in a very different context. I will not talk about conformal field theory, and we will not use it. What is important is the specific form of functions J and U. You can see it in the green box in the bottom of the slide. So this is a simple harmonic time dependence with frequency omega. Well, and it turns out that this conformal quantum point contact model is exactly solvable in the sense I will clarify a few slides later. Since we have a time periodic Hamiltonian, there is a special tool designated to deal with such Hamiltonians, namely the Floquet theory for periodically driven quantum systems. The Floquet theory tells us that if we are interested in evolution in stroboscopic times, namely if we are interested in the moments of time which are just simple integers of our period, then we can in a way replace our actual original time-dependent Hamiltonian by a fixture's so-called Floquet Hamiltonian. Importantly, the Floquet Hamiltonian doesn't depend on time. So this means that we can remove one layer of complexity from our far from equilibrium-driven quantum manybody dynamical problem. Namely, we can remove the dynamical layer of complexity. This means that apparently we can replace differential equations with variable coefficients with differential equations with constant coefficients, which is good, as I have explained. However, unfortunately, typically Floquet Hamiltonians are not known, and the problem of calculating the Floquet Hamiltonian is as complex as the problem of solving the original dynamical problem, which is bad. So in general, Floquet theory, I would say, does not add much relief to our complexity trouble. However, in our exactly solvable model, we can find the Floquet Hamiltonian exactly. And this is the main insight of our research project, the main theoretical insight. The root cause for this is the unitary transformation of the Hamiltonian, which is shown in the upper equation. It tells you that your time-dependent Hamiltonian can be obtained from the Hamiltonian in the initial moment of time by means of a unitary rotation with the generator sigma capital, which is again a quadratic fermionic operator of a simple structure shown in the second equation. Probably instead of staring at equations, it's better to look at the figures on the right part of the slide. The upper figure shows the original Hamiltonian, which is time-dependent, thus these wiggly lines in the center of this figure. And the lower Hamiltonian shows the the lower figure shows the Floquet Hamiltonian. It is time-independent, there are no wiggly lines. However, there are highly non-local hopings in this Hamiltonian. So a particle, this generator capital sigma induces hopings from between two distant edges of the two chains, as you can see. It is actually quite a non-trivial fact that a local driving concentrated just on two central sites induces a highly non-local hopings in the Floquet Hamiltonian. Now we have a time-independent Floquet Hamiltonian, we know it exactly, and we can attempt to solve the problem. Fortunately, our fermions are not interacting, and non-interacting quadratic fermionic Hamiltonian can be solved exactly by standard techniques, and this is what we do. We focus on two particular observables. The first one is the heating rate. This is how much heat is pumped in the system by the external fields per unit time. And the second quantity is the current through the quantum point contact. Both are averaged over the cycle, over the period. And we start from the initial conditions when the left chain is, say, completely filled and the right chain is completely empty. You can see what happens in the movie on this slide. So initially all the fermions are concentrated in the left, then they start to flow to the right chain. There are some oscillations in the center. So the movie shows just the average probability to find a fermion per site. And you can see a steady current which is established after a brief transient period of time. The number of fermions in the left chain diminishes, the number of fermions in the right chain grows. And we can produce exact formulas for these two quantities. They are shown on this slide. They depend on the initial densities of the fermions in the left and the right chains respectively, rho left and rho right. And also the heating rate depends on the heating function gamma, and the current depends on the transmission coefficient T. Both these quantities depend on energy and also on the frequency as a parameter. To scare you a little bit, I will show the explicit formula for this T and gamma, but you don't need actually to stare much at this formula. the most important feature of this formula is that the heating rate function gamma is identically 0 for any energy as long as the frequency is greater than the critical frequency, which is in our notations, in our units, is just equal to 2. So whenever the frequency is greater than 2, then the heating rate function gamma is 0, and therefore the heating rate is 0. This means that despite the system is vigorously shaken, is vigorously driven, there is no heating. This is quite opposite to our everyday experience. We know that if we shake something, or if we rub something, or if we stir something, this something gets heated, and the more we stir, the faster it heats. However, it turns out that in quantum world, this doesn't happen indefinitely. If we increase the stirring or the shaking frequency even more, the heating decreases. This tendency to decrease of decreasing the heating rate is well known. However, what we find here is that the heat not just decreases, it is just identically 0 above the critical frequency. This means that we have found a phase transition. A phase transition is, broadly speaking, an abrupt change of some pattern of behavior of the system when varying some parameter. Okay, so we have established this, and now remember I have told you that integral models can display non-generic behavior, and it was natural to ask whether this is a peculiar feature of this exactly solvable model, or this phase transition is there for other models. So we have checked this numerically, and we have found that for all models that we have studied, I mean for all time dependencies of functions j and u, we find that this phase transition is there. There is no heating above the critical frequency, and the critical frequency is the same. Let me emphasize that this is still non-interacting fermions, so we could do numerics quite easily. Non-interacting fermions are easy to simulate numerically, in contrast to a generic case. And so we have found this. This is good, but we have also found something even more interesting. For a different quantum point contact, which we call tunneling quantum point contact, that is defined by non-vanishing periodic hopping amplitude j and 0 on-site potentials, we see that not only the heating rate but also the current vanishes above the critical frequency. This is also surprising actually, because imagine you have two reservoirs and you have a tube connecting these reservoirs, and naturally if one reservoir is full and another one is empty, the liquid would flow through the tube. Now if you start shaking the tube, you don't expect that the flow will stop. However, here in the quantum setting, the flow does stop. Let me demonstrate the difference between our exactly solvable quantum point contact, conformal quantum point contact, and this tunneling quantum point contact. In this movie, you see that in the first case, in the upper plot, the fermions do flow from left to right, while in the bottom plot, the fermions do not. There is some initial small transient period when a couple of fermions do flow through the quantum point contact. However, after a very short time, this transient current halts and there is no current at all. In contrast to halting the heating rate, here we cannot use the exactly solvable model because this happens not in a different model. So we have many questions unanswered about this effect. What are the exact conditions for it to happen? We have checked various quantum point contacts numerically, and we have seen that in some quantum point contacts the current does flow, and in some other it doesn't. What are the conditions for this effect to take place? Well, we have pinpointed empirically a set of conditions which seems to be sufficient for the effect to take place. They are formulated on the slide in terms of the functions j and u, of the properties of these functions. However, we also see that these conditions are not necessary. And the question, what are the actual conditions and what is the nature of this effect, remains open. Now, as I have promised, we have also used our exactly solvable model to test two approximate techniques. The first one is the Floquet-Magnus expansion. It is an expansion in powers of the inverse frequency. So it is assumed to work at large frequencies. And you can see first three terms of this expansion written shown in the slide. You can try to apply this expansion term by term to a problem. And you can try to see what approximate Floquet Hamiltonian it produces. And it turns out that it produces a Floquet Hamiltonian which is very different from the exact one which we know from the exactly solvable model. Namely, each iteration of this approximation produces only local hoppings first between two neighboring sites, then between two next to nearest neighboring sites, and so on and so forth. However, you need to increase the number of iterations to L, which is the system size, to get something at least similar to the exact Floquet Hamiltonian. So this indicates that the Floquet-Magnus expansion is not actually good for this problem. For experts, I would mention that this actually does not prove this because the Floquet Hamiltonian is not defined uniquely. However, we regard this as a strong indication that something is wrong with the Floquet-Magnus theory applied to this particular problem. This is not of much surprise, actually. It was known that the Floquet-Magnus has problems with non-interacting manybody systems. The situation was not quite clear for quadratic fermionic systems. And here we actually make an argument that it doesn't work well in this case also. A different technique which we can try, which we can attempt to use here is the perturbation theory. We calculated the heat rate and the current in the first order of the perturbation theory. And we have found that while at low frequencies, it works quite well whenever the V term in the Hamiltonian is small. However, it is not able to discriminate between the cases where the current flows and the current holds above the critical frequency. So this means that even if the current flows above the critical frequency, it is described by the higher order of perturbation theory, namely the fourth order here. And the leading order perturbation theory isn't enough to shed light on this effect. We weren't persistent enough to go to the next order of the perturbation theory. However, this is on our to-do list. Well, what happens now? A next natural question to ask is what happens to interacting fermions? Interacting fermions are more like a model of interacting fermions is more like real-world description of this of real electrons, because electrons are strong interacting due to Coulomb interactions. This is actually work in progress. Some tentative results go as follows. So we are quite sure that if the interactions are switched on only inside the quantum point contact, then all the effects remain. One could argue that this is not a very realistic situation, because real electrons interact everywhere, not just inside the quantum point contact. However, it is known that in many situations this is a quite fair description of your system. If the interactions are switched on everywhere, I mean in the bulk of the conductor, then we suspect that the current and heating rate are not completely absent above the critical frequency. However, they are strongly suppressed. Well, as I have said, still this is a work in progress, and we also plan to shed light on this question. Possible applications. As I have advertised in the beginning, we have a sort of anticipation that these effects might be useful in applications. Why? First of all, absence of heating is almost always welcome. So you don't wish your devices to heat, to waste energy, to require cooling, and so on. Therefore, our effect of complete suppression of the heating can find rather straightforward applications. For example, if you have some quantum point contact which you need to drive anyway, then you might wish to tune your driving frequency so that it is higher than the critical frequency. In this case, the heating will be completely absent. And second, switching of the current by frequency may be also useful things. Actually, the whole field of electronics is about manipulating electrical currents. And the more handles you have to manipulate the electrical current, the better. The more options you have as an engineer. And we add actually one more handle to the already rich toolbox of engineers. Namely, we add a possibility to control the current by varying the frequency. So I have actually came to the summary. We have discovered an exactly solvable model for a driven quantum point contact. This exactly solvable model have turned out to be quite useful. It predicts effects that are generic, that is, that are present in other quantum point contact models that are not exactly solvable. The main effect which has been discovered is a quantum phase transition above a critical frequency. This phase transition, as I have said, is there for non-exactly solvable models as well. The heating rate always is absent above the critical frequency, and the current is absent for some models, but not for all of them. We don't understand many things at the moment. We don't understand the conditions for current vanishing. We don't understand exactly what happens if we add interactions to our model. We don't understand what happens if we replace our one-dimensional conductors by two-dimensional conductors, although here we can anticipate that the effects will stay there because it is the quantum point contact, not the conductors, which play the major role in the effect. And also we anticipate that a frequency-controlled quantum switch can be constructed based on this effect. Let me thank the Russian Science Foundation for funding the research project which I'm involved in, and this study of the quantum point contact was made in the framework of this larger research project. Since I have some time, let me make a postscriptum. You know, if you have a good tool, you would love to use it for various purposes. Now we have this conformal quantum point contact model, which is exactly solvable. We have used it to study quantum transport, but also we can use it for different purposes. And we are actually using it for benchmarking quantum speed limits and adiabatic conditions for manybody systems in the framework of another project. Quantum speed limits are rigorous estimates on how fast the quantum system can evolve. And one is often interested in whether these quantum speed limits are tight. Do they produce a good estimate or a bad estimate? And we can actually apply them to an exactly solvable model and see what sort of estimates they produce. This is the same case with adiabatic conditions. Adiabatic conditions are conditions which tell you how slow you should drive your system in order for the system to stay in an instantaneous eigenstate, simply put, close to equilibrium. There is also a range of these conditions, and the things turn out to be quite complicated for manybody systems. Still, there are some conditions appeared quite recently, and the same question arises, whether they are tight, whether they are good. And we also use various integrable models, in particular this one, to test these rigorous conditions, whether they perform tight in a realistic manybody model. Now let me thank you for your attention. We have almost half an hour for questions, and the questions are welcome. Yeah? Is it theoretically possible to reach 100 iron content in iron powder? I think this is a question to the previous speaker. This is my guess. And the second one is also about some chemical substances. I think both questions are for previous speaker. Yeah. Yeah, then let me thank you once again for your attention, and good luck in your research.